Welcome to the 1938 Nobel Prize in Physics, which went to Enrico Fermi. Now, Fermi died relatively young. He died in 1954. He was just 53 years old. Passed away from stomach cancer, probably brought on from long-term exposure to radiation. He was actually vocal about the fact that he felt the risks were worth the reward. But that's neither here nor there. So he won the prize for a couple of things, and the official prize announcement was kind of interestingly phrased. It says that he won the prize for his demonstration of the existence of new radioactive elements produced by neutron irradiation, and for his related discovery of nuclear reactions brought about by slow neutrons. And what the heck does all that mean? We'll get to all that as we go through this video. It'll become very clear, and I hope you'll enjoy it. But the interesting thing that you can take away from that, just sort of by listening to it, is how did the dude create new elements? He looked at the periodic table of elements and said, there's not enough stuff here. Let's go build some new ones. He didn't really set out to do that, but through his work in nuclear physics, it became obvious that you could. So what he did was he used some of what he knew about the way the nuclear process worked. He went into the lab, he did things, and eventually out come these new elements that are either not found in nature or they're found in very tiny trace amounts and almost impossible to see. So he found a way to synthetically create elements, which is one of those things that if you think about it, it's just bizarre to think you can actually turn one thing into another, but that's what nuclear reactions do. So let's dig into the career and Nobel Prize of Enrico Fermi. Now, he was actually known for quite a few things. The list is actually just impressive, as you can imagine. He's known for his theories on beta decay, a thing called Thomas Fermi scattering, the Thomas Fermi model, Fermi method, Fermi paradox, Fermi's golden rule, Fermi-Dirac statistics, Fermi gas, fermion, and demonstrating the first self-sustaining nuclear chain reaction. On top of all that, he created some synthetic elements and added entries into the periodic table as we know it. So let's just sort of start with an easy one, the nuclear chain reaction. Okay, it's not really that easy, but how did he actually pull that off? Well, let's take a look. Now, a nuclear chain reaction is what you see here, and you'll notice it says uranium-235 instead of 238, which there is a difference. There's a difference in between those two, and that's a subject for a whole different video. But 235 is what you use in both nuclear reactors and nuclear weapons. It is purified much differently in both cases, but it's the one you want to use. And the reason you have to induce a reaction in it is because it decays, but it decays very slowly compared to what you want to produce any kind of real energy. So it decays. Its half-life, as it naturally occurs, is about 700,000 or so years, give or take. And that means how much time does it take for half of your sample to decay into something else? So to be useful for a reactor, you want to speed that reaction rate up. But obviously, you want to be able to very carefully speed that reaction rate up, or you wind up with a nuclear runaway reaction. You don't want it to go too far too fast, otherwise you have problems. So when you look at this induced sustained reaction, what Fermi figured out was that if you introduce slow neutrons, I'll explain those in a minute, it comes in and every once in a while one will impact the nucleus of a uranium-235 atom, inducing extra fissions, and it causes it to break into two pieces. And in that process, it releases energy. So the neutron comes in, splits the atom does what it's going to do, it falls into pieces, it goes through this chain reaction, and out the other end come atoms that are not as big as the original ones. So what happens is in this process, you lose a little bit of mass. And when that mass goes away, it gets released in the form of energy. E = mc squared. Thank you, Professor Einstein. Now, when you see things like in the movie Oppenheimer where they have to make uranium, well, what they're doing is they're purifying uranium-235 out of all naturally occurring uranium, which includes uranium-238. Uranium-238, as it turns out, is 99.3% of all uranium on planet Earth is 238. It is always mixed with 235, so you have to separate out the isotope that you want. and the isotope that you want is only about 0.7%, give or take, a little bit less maybe, of the overall sample. So to separate those two becomes very difficult. That's where you need large lab equipment with centrifuges or cyclotrons or all kinds of other gear that's really expensive to build, and it takes a long time to run to separate out enough 235 to run a reactor. Now also, I want to point out that the purification levels need to run a reactor and the purification levels needed to build weapons are entirely different. It needs to be a much more pure sample to get to weapons grade. So if you ever had that fear that, well, gee, maybe somebody could take the uranium from a reactor and build a bomb, they can't. They have to purify it even further. And there's also lots of other reasons you can't do that. But you can't just take one and go build the other out of it. It's not the way this stuff works. So this reaction itself is what enabled the nuclear age to build nuclear reactors that the Navy uses all the time in their larger vessels. Some countries are largely nuclear powered. The United States has nuclear reactors around. We're currently building more. But if we didn't understand how to get this sustained reaction, we would have never gotten there. So let's look at what a slow-moving neutron is, because it's kind of key to this whole process. So a slow-moving neutron is central to this entire thing working. Without that, we're not getting anywhere. So the average speed, and don't worry about units. Physicists sometimes use units that don't make much sense unless you're in a lab. But the average speed of a neutron is around what's called 5.5 MeV. The average energy level of a slow-moving neutron is 100 eV or less. So you got to slow it way down. Well, why do you want to do that? Well, if you're moving too quickly as a neutron, remember these are neutrally charged particles. They don't really interact with electric fields at all. They're not attracted to them. They're not repulsed by them. They have no charge. They don't care that the field is there. They don't care that the electron is there, the proton is there. They just don't care. So the faster they're moving, the more likely they're going to penetrate right through a sample and not even slow down. They're not going to stop. They're not going to say hello. They're not going to come in for dinner. They're just going to go right through. You have to slow them down so that they'll actually interact with things in some cases. And that's the goal here. Now that's done using paraffin wax, which is just a hydrocarbon. Now the hydrocarbon is not involved in the nuclear reaction at all. It's just a method of slowing down that neutron and putting it into a mode or a speed in which it will interact and cause that nuclear chain reaction. Now the transuranic elements are things bigger than uranium. They're things that didn't exist. They hadn't been found. And if you look at uranium on the bottom of the chart there, you'll see it's right there under number 92. It's in green, sort of fourth from the left. But if you look two to the right, you'll see this thing called plutonium. Now, plutonium was first observed in 1941 at the RAD lab in University of California, Berkeley. It was discovered by Glenn Seaborg, Edward McMillan, Joseph Kennedy, Arthur Wall. And what these gentlemen were doing was continuing the work of Fermi and others who showed ways to split the atom and do it sustainably, or to have neutron capture occur and have new atoms made, or have these nuclear reactions occur where other atoms are the outcome. And one of the ones that came out of that was plutonium. Obviously, plutonium is useful for lots of different things, including weapons. But the secret of plutonium was actually kept. It was discovered in 41, and it was not informed into the rest of the scientific community. Nobody else knew about it outside of Berkeley and the Manhattan Project and some very tightly held military guys until after World War II. So these discoveries weren't just, scientists running around going, oh, I found this thing, we're going to go tell the world. They were doing things in a way that actually did kind of keep secrets where they needed to be kept. So I don't want everybody to realize that even in the face of a potentially huge prize-winning discovery, that secret was actually kept for years until the surrender of the Japanese at the end of World War II. So this Nobel Prize and several others around this time period were won by people who had direct involvement in the birth of the nuclear age, and Fermi in particular had direct involvement in the Manhattan Project. And so did some of the other winners, and a lot of other people. Now, I wanted to make a couple things very clear that aren't necessarily all that clear, but not hard to find, not protected, not classified, not hidden in any way from the general public. Uranium and plutonium can both be used to build weapons. That's not a secret. There are other radioactive elements, especially in the actinides, that can be used for that as well. Uranium and plutonium are just the easiest to do that with. Now, uranium is used in both reactors and weapons, and I would say the only one of those two that's a valid use is a reactor. One of the reasons that reactors are so tightly secured and so carefully kept track of and have inspections and international coalitions and decisions and all kinds of stuff is that as a byproduct of uranium, you get a lot of weird byproducts that come out the other side. One of those that comes out of a uranium reaction is plutonium, because when uranium undergoes neutron capture, sometimes you wind up with plutonium on the other side. So in that spent fuel is plutonium. Now, plutonium has more uses than just building weapons of mass destruction. You can actually use it in other reactors to produce power as well. One of the things that can be done with modern technology that couldn't be done then is keeping track of that material and making sure it's used up and all kinds of other stuff that would keep it safe and out of the hands of people that would build weapons with it. Now, the thing that I wanted to bring to everyone's attention is that the nuclear world is not that old. It's less than 100 years old. Hydrocarbons have been around a long time. Coal, natural gas, all these things have been around for hundreds of years. The nuclear world has not been around that long in the history of man. It's new. And if you look at it, how far we've come since it was sort of discovered, we've come a long way. And reactors with modern designs are significantly different than reactors with, say, a Chernobyl design or a Three Mile Island design, or even a Fukushima design, because that one was, I think, from the 80s. And it's not, the 80s anymore. We're 40 years later with a lot of new safety gear. The Navy puts reactors on moving vessels in the ocean, and they don't have issues. In fact, a lot of modern navies do that. Reactors are typically very boring places to work. They do need to be monitored. They do need to be tracked because there's plutonium coming out the other side. Now, if we were smart enough and agreed with enough things and didn't have enough regulatory problems, we would use the decay products from a uranium reactor into other types of reactors. And we would get them off the surface of the planet because we're just burning them out using other types of reactions. So rather than storing it, they are useful things. You can use, especially the plutonium, in other reactors. So the stuff is not to be feared, it's to be respected. And yes, there have been some accidents, but remember, this stuff is, it's barely 100 years old at this point. So we've come a very long way in what is relatively a short period of time. And over the last 40 or 50 years, the funding to nuclear research and to nuclear projects and to even looking at new stuff has been cut pretty hard. And not for any other reason than it was. I mean, I think there's a lot of misunderstandings. There's certainly a lot of public outcry whenever there's an accident, and rightfully so. That needs to be handled very carefully. And different types of reactor designs like thorium and others should be examined, because if you really want to have a world that is free of hydrocarbon use, this is one of the ways to do it. You don't use hydrocarbons in these reactions. And solar is great, wind is great, where they use wave energy is great, but it's not going to satisfy the electrical needs of the entire planet. Nuclear gives you a lot more output than the other sources do, and is about the only thing, if you do the math, that has enough output energy to really, I think, replace the dependency on fossil fuels. Electric car is great, but depending on how you power that electric car, you still might be using a gas power plant to power it. You're still on a hydrocarbon. So nuclear is one of the things that needs to be taken more seriously than it has been. And I think the scientists are ready to do that. I know I myself, I'd work with it in a minute. It wouldn't bother me in the least, and it can be done safely. And I've worked with some of them. I've been around high powers or high radioactive sources, and I'm fine. So it is something that I think needs to have a brighter future than it does. And I think, yes, it can be made into weapons, but so can hydrocarbons, so can regular explosives, so can anything with hydrogen. It's not that hard to turn into a bomb. So I think we do need to pay very careful attention to how it's used, but I think it also does need to become a far greater part of the mix of the world's power plan going forward. So everybody's enjoyed this video. There are more nuclear projects coming up. There are a couple of years where there was no Nobel Prize. We're sort of at the height of World War II, but we're coming up on the more modern ones, so it's exciting stuff. I hope everybody's enjoyed Fermi. He was an incredible guy. If you dig into his work beyond just the Nobel Prize, it's shocking stuff. So everybody have a great day. Please don't forget to click like and subscribe and all that fun stuff. It helps us out with the algorithms, and we'll see you on the next one.